As I said, just a session on what are some cool things that you might want to look into, some parts of machine learning, some words that are commonly thrown around that you might want to understand. And the session basically has three quick parts. The three quick parts are: one, different types of activation functions; two, different types of cost functions; and three, different types of optimization algorithms. So in each of those categories, we've learned about sigmoid activation functions, the mean squared error cost algorithm, and then gradient descent for the optimization algorithm. I'm going to show you a few other possibilities that you might come across, when you're out there on your AI adventures. And I'll also leave a few possibilities for you to look into yourself. So let's just get started with the first section on different activation functions. This will be pretty short. So if you remember, when it comes to the activation function, we use this when we were doing logistic regression. So we had a weighted input that we created with some parameters theta and the input x. We passed it into the sigmoid function, which is just one type of activation function. And the output from an activation function, we call it the activation, and we ran that to get y hat. So remember, the sigmoid function, you don't need to remember the formula, but it's here. You don't need to remember the derivative, but it's here. What it basically does is you pass in a number x, and it squishes it between 0 and 1. And that's why the sigmoid function is pretty useful for binary classification, where, we want to return a 0 or 1 at the end. That might be, okay, does the patient get, cardiac disease over the next 10 years or not? So that's pretty simple. However, the thing is that the sigmoid function, it's not the only activation function. And depending on what we want to do, what type of problem we're working on, there might be other activation functions that are a little bit more suitable. So in general, this is actually the notation that we use when we're defining these equations. We have this activation function written as g of z. I don't know why it's g. Machine learning literature is weird. We do have this function g of z, and we can set it to different activation functions. So for example, we could say g of z is equal to sigmoid of z. And that would do the same thing as here. But we can also set it to some other functions. Any questions before I get into the other functions? All right, so let's do it. The first other function, it'll start off a little bit simple. You won't get like a messy formula like this, so yay for that. The first function is called the rectified linear unit, which is a fancy name, but it's not too hard. So we often write it as ReLU, and we call it ReLU often too, rectified linear unit. And this function just chooses whatever is larger, the input x or 0. So, if we have x is equal to -5, then it will return 0, because 0 is larger. If we have x is equal to 100, it will return x, because 100 is larger. So I'll show you what this looks like on a graph, just for intuition's sake. The rectified linear unit, so you have x as the input, and then ReLU of x as the output. So notice, when you have inputs that are less than 0, well, you just get back 0. And then after that, you pass in 2, you get out 2. You pass in 4, you get out 4. You pass in 6, you get out 6. So you can think of the rectified linear unit function as basically no negatives allowed, okay? You can put a negative here. It's like getting rid of all the negativity. No negatives allowed. This is a very positive, happy vibes function. Make sense? So why might you want to use this happy, positive vibe function? Well, if you think back to our regression problems, so the regression examples I gave you, they were predict the price of a house, predict the price of a car. Well, you really don't want your algorithm to predict like a negative value for your house or your car. That doesn't really make sense. So up here, when we were doing binary classification, we didn't want, values beyond the 0 to 1 range. So we used the sigmoid function. Well, if we have regression problems, like predict the value of a house or a car, then we might do this, and we might set g of z equal to ReLU of z. We might set it to the ReLU function, just to make sure we get a positive outcome. Make sense? Now keep in mind here, I'm going to show you, why we're using these derivative terms. So why it's important that we know the derivatives of each of these functions. But for the ReLU function, here is the derivative. The derivative, if you just have 0, 0 is a constant, so you just get 0. If you have another number, so if you have some value x, then if you try to derive x, it's just like 1 times x. So you just get out the derivative 1. If you look back at the derivation lessons, you'll see what that is, but if not, you don't need to worry too much. Just keep these values as assumed, and it's just the same as how, if you wanted, I could show you the derivation for this, but if not, you can just use it. So with that said, that is the ReLU function. One thing to keep in mind, if x is actually equal to 0, just choose either of these values. Make sense? Sound good? All right, ReLU function done. Let's do one more activation function, and then I'll give you some to look into yourself. This other activation function, it's called, okay, it's going to be a messy equation. So just, take a deep breath, calm down. It's going to be messy, I'm telling you. So it's called the hypertangent function. We write it as tan h of x. The hypertangent function, it looks like this. And that looks a bit messy. It looks a bit ugly, I know. And it has this, derivative. And, it's not too bad, but yeah, still not very understandable. Why is this? So I'm actually, instead of showing you the equations, I'm just going to show you the visual so you can understand what this does. So the tan h function, hypertangent function, it looks at, x as input, tan h x as output. It looks very much like the sigmoid activation function, except sigmoid is from 0 to 1, and the tan h function, it's from -1 to 1. You see here, -1 to 1. Now this might sound like a tiny distinction, but it's actually really useful for a function to be able to have negative values. Now, unfortunately, I can't tell you fully how useful it is, because a big part of its use is with actually neural networks. However, I'll give you a oversimplified use case of why you might, want to use this. So let's say you're making a self-driving car algorithm, and for some reason you're doing it with some kind of regression. Now, it's not going to be, logistic regression where you get out a value from 0 to 1. Instead, we're going to set the activation function to the tan h function, where you get out a value from 1 to -1. Now, a use case for this might be, let's say you have a steering wheel of the car, this is 0 degrees. You can either, you can have positive degree changes, so you can go this way. So let's say you go 1 degree this way, as 0.01 seconds, then another degree this way at 0.02 seconds, and another degree this way at 0.3 seconds. And the algorithm, it's like predicting, okay, should I go like 1 degree this way or -1 degrees? Should I go that way? So it might be like, oh, you have a steering wheel and you're predicting, which degree to turn the steering wheel in. Now this is oversimplified, and this is like, just keep in mind, no one would actually do that. But you can think of situations like that where you might have 1 or -1 as an output range. Do you want some value to go up or do you want it to go down? That's one use case of the tanh function. Another use case that you'll see about, what is the main reason people use this will come when we explore neural networks next week. So just keep that in mind. Now, that being said, I did finally want to tell you, why am I giving you these derivative terms for the ReLU and the tanh functions? Remember, when we're doing backpropagation, here's what's going on. So we're calculating partial C by partial theta, some theta j. So it could be theta 0, theta 1, theta 2. We do it with this chain rule, cancel that, cancel that, cancel that, cancel that, and we're left with partial C by partial theta j. And we do it for, all the theta j's from 0 to n. N is the number of parameters. So remember, this was you've probably seen this, 3, 4 times now. This is the derivative for each part. And when we did this computation, well, I just, plugged in over here. You'll recognize this as the sigmoid derivative from up here. However, it's not always going to be the sigmoid derivative. So if you have, you're using a tanh activation, then you're going to have this derivative. If you're using a ReLU activation, you're going to have this derivative. So this is just to say that in backpropagation, you'll need to know the values of these functions. So instead of writing, this sigmoid thing, I'm just going to cut that out, and I'm going to put the general, formula here, which would be that you take whatever activation function you have, and you, put in its derivative, g prime. Remember that's derivative notation, g prime of this term right here. X at the ith example for the jth input feature. So instead of just having, the sigmoid derivative be plugged in here, we can have all of these derivatives depending on what the activation function is. Making sense? So these formulas, they're just for you to know so that when you're doing backpropagation, then you can plug in the right values over here. And that is basically the end of, the activation function section. There are these two other activation functions, which I'll leave for you to research. So search up, leaky ReLU linear activation function, and go learn, what do they look like? What is their derivative? What is their actual formula? And what is their use case? Why would we want to use a leaky ReLU function versus a ReLU function, for example? And the same with the linear. Cool. All right, that's the first section done. 1 out of 3. Yay. Different cost functions. That's part 2. Here, we already know one cost function, which is mean squared error. Here's the mean part, taking the average. sum across all m examples, divide by m. Here's the squared part, you see, we have a little squared right here. And here's the error part. You figure out what is the difference between the prediction and the actual label, y. So this function, I originally just used it for everything because it was pretty simple, pretty intuitive. However, there are some, let's say, drawbacks here. So I've told you about twice now, this is not a great function to use for logistic regression. The reason is that, let's say our prediction is something like 0. Let's say 0.2, and the actual label is 0. Yeah? So we want to adjust our data parameters so that we get a better prediction, we get it closer to 0. But look at the cost, it's 0.2 minus 0, we square that, and it's like the cost becomes even smaller. It becomes 0.04. That's pretty unintuitive. That's not good behavior. This does not look good. So in general, whenever you have a logistic regression problem, you do not want to use the mean squared error function. Why? Because when you just have values between 0 and 1, then the difference is, they usually just end up getting smaller when you're squaring everything. So not a great function. Another note that I want to tell you is in these equations up here, I often say, yeah, so y hat is like the rounded version of the activation. And that's true, right? So you have 0.2. If you get that activation here, then your algorithm is going to predict 0 as y hat. However, especially when you're doing, logistic regression and, the difference between the numbers is so small, it's only from 0 to 1, that range, you really don't want to round, these values, these activation values, before you pass it in to the activation function. So honestly, I know it says y hat here, but just pass in the activation values and then just round at the end. Imagine you're just, giving an extra little bit of precision, instead of doing 0.99, instead of putting like 1, you're putting in 0.99. So it's not too big of a difference, but it's just, giving you a little bit more precision in the cost functions. So round at the end. Don't round, up here and then pass in the y hat value, which is the rounded version, just round at the end, just for a little bit more precision. Now, with that being said, why do we actually use the mean squared error function? It's pretty useful, just not for, 0 to 1 ranges. So just not for the sigmoid function. When you use the sigmoid function as an activation function, don't use the cost function mean squared error. However, imagine like you have housing prices, like you predicted a housing price of 420K. That's a pretty big number. And then, oh, by the way, K just means 1,000 for 20K, and like the actual housing price was 400K. So that will give you a difference of 20,000. And then when you square that, 20,000 squared, the cost gets pretty big. So the cost function is doing what we want. It's saying, hey, no, you can't be 20,000 units off. That's too big. So when you're doing regression, cost function fine. When you're doing logistic regression, no, not mean squared error. Making sense? All right, so mean squared error, good for regression. What about if we, do want to do logistic regression? What should we use? So remember, there's logistic regression. It's used for classification problems, especially binary classification problems. So when it comes to binary classification problems, we have a specific cost function called binary cross entropy. Remember, binary just means, 0 or 1. Did the patient have a heart disease or not? And this function, it's going to use the logarithm. If you know what that is in math, great. If you don't, here's a quick explanation, quick reminder. If you have the log function and you're taking log at x, what that means is 10 to the what power is equal to x. So for example, let's say you're taking the log of 100, then 10 squared is equal to 100. So the log of 100 returns 2. It returns the exponent to which you're raising 10 so that you can get this input x. Another example, let's say you're doing log of 1,000, then it's asking 10 to what power equals 1,000. So it would be 10 to the third power is equal to 1,000, so log of 1,000 would return 3. Making sense? All right. I'm also gonna graph the log function for you, just so you get some intuition about how this formula is gonna work. So y is equal to log of x, the vertical is the y-axis, horizontal is the x-axis. I'm specifically graphing this over the range 0 to 1, because the cost function, it's gonna get predictions between 0 to 1. We're gonna use it for binary. Now notice this. When we have an input of 1 to the log function, then the value we get is basically 0. And then the closer we get to 0, the value is basically negative infinity. So the closer the input is to 0, the bigger the value is in the negative direction. The closer the input is to 1, the closer the value is to 0. Make sense? So keep these two things in mind. This is how the log function works. Close to 0, big negative value. Close to 1, value that's almost 0. Now let's take a look at the formula. So we have, first of all, not too bad, okay? We're just, taking the average across, taking the mean across a bunch of examples, so not too bad so far. Now, what are we actually taking the average of across all the examples? It depends on if the label is 1 or 0. Okay, let me say that again. The binary cross entropy function, it works by giving a different value for when we're predicting a positive output and when we're predicting a negative output. So if the patient gets heart disease, it's going to return a different value than if the patient does not. This is not a prediction, this is y. So if y is equal to 0, then we're going to get one value. If y is equal to 1, we're going to get another value. Making sense? So let's look at what it is. Here's the first part. This is what happens if y is equal to 1. Now, why is that? Well, because, y can be 0 or 1. However, we're multiplying over here, y at I. So if y were 0, then this entire term, it would just be equal to 0. So when y is equal to 0, this value does not apply. However, if y is equal to 1, then it's just 1 times this term. So this is the important term. So take a look at what's going on. Remember, log, we're passing in the prediction as the input. It will give a value that's nearly equal to 0 when, in this case, the prediction is equal to 1. So if the prediction is almost equal to 1, the output is nearly equal to 0. And if you think about it, that's what we want, because we just said y in this case would have to be equal to 1. If it were equal to 0, then this entire thing would be 0. So if y is equal to 1, then we want the prediction to be equal to 1. If the label and the prediction are equal to 1, then the cost is almost 0. That's what we want. We're saying, hey, you're doing pretty good. Label is 0, prediction is 0. So that's how this part works. Make sense? Now we're going to have another part. This is for when y is equal to 0. Why is that? Well, consider again. So let's say we substituted 1 here. So for this, we had y is equal to 1. Then 1 minus 1, that is equal to 0. And 0 times, whatever is just still 0. So what I'm saying here is this term, it can't have y equal to 1. Otherwise, that value is 0. However, if this term is equal to, it has y equal to 0, then 1 minus 0, that's just 1. So it's like you're multiplying 1 times whatever is in here. So this value only comes out when y is equal to 0. Now, so we're saying here y is equal to 0. Then we want y hat to be equal to 0. Look what happens. If we have 1 minus 0, then the input to the log function will be 1. And that's what we just said. Hey, like when the input is 1, then the output is close to 0. So if, the algorithm predicts correctly, the label is 0 and the prediction is 0, then we're going to get back a pretty small cost, basically 0. However, if, the algorithm does the complete opposite, it does, yeah, whatever, I don't care if the label is 0, I'm going to predict 1, then the algorithm is going to freak out because like 1 minus 1, that's 0. And you can see here, well, the closer you get to 0, the higher the cost becomes. So the closer you get to 0, the bigger the cost becomes, just in the negative direction. So if the log actually does become close to 0 because you predicted the wrong thing, then you're going to get back a pretty large cost. Making sense? Any questions?
Wait, so could you go to the graph again?
Sure. Here's the graph.
So what were you saying again when you're like, if the prediction is 1, then the cost is 0? Could you put
Yeah.
that?
So remember, y is equal to log of x. So on the x direction here, I'm passing in the prediction, right?
Yeah.
So whenever, the input is 1, then the output is 0. So the cost I'm getting is 0. Now in this case, y must be equal to 1, and the prediction we want it to be equal to 1. So if the prediction actually is equal to 1, then we're going to get back a very low cost, yeah?
Yeah.
In this case, this is only going to work if y is equal to 0, and we want this y to be equal to 0. So then 1 minus 0, that's just still 1. And if we take the log of 1 again, then it's going to give us a very low cost. However, if we do the wrong prediction, so for example, we predicted 1, but the label was 0, then 1 minus 1, then we're going to take the log of 0. As you can see here, the closer we get to 0, the bigger the cost gets in the negative direction.
Okay. Yeah.
Now, just keep one thing in mind here. Notice, like when the algorithm gets it wrong, we're giving it a very large negative cost. That's really weird. So that's why over here I have this negative 1. At the end, we multiply all of these negative values by negative 1 so that we get a positive loss. Up here, we didn't have the negative 1. Down here, we do, just to make sure that when we get these negative values, that we end up, flipping them to positive cost. So that is, again, binary cross entropy. It's for when we have 0 or 1s. Now remember, it might not just be that we have two, outputs. We might have, okay, car, camera, looking out at the road. Am I seeing a pedestrian, a stop sign, or a bicycle? or another car. You know, we might have 4 outputs. So we have a general version of the binary cross entropy algorithm. It works for any amount of, any amount of predictions, any amount of classes, as we call them. So this is just called cross entropy loss. This is binary cross entropy loss. This one, it works on the same principle up here. So, same formula, basically, except we don't have, the latter term for just 0. The reason is it sorts itself out. You don't pass scalars into this function, you pass in vectors. So over here, let's say you now have 3 classes. I'm saying the 0th class is 0, the first class is 0, and the second class is 1. So maybe no, there is no stop sign, no, there is no bicycle, but yes, there is another car that I see, in the computer vision. And just like we have these 3 labels, we're also going to have y hat generate, 0 to 1 values for its predictions. So, over here it's thinking, oh yeah, I think there's probably a pedestrian in the image. Oh yeah, I probably think there's a car, in the image, but no, I don't think there's a stop sign. So we have scalar inputs up here. That's just like one value, like 1 or 0. But over here we have a vector. Now what we do is we just do the element-wise log across all of these. So remember, if this is close to 1, then we will get a we will get a small value. If this is close to 1, we will get a small value. If this is close to 1, we will get a small value. If this is close to 0, we will get a large value. Yeah? Because it's just the log, Input close to 1, you get a value close to 0. Input close to 0, you get a value that's very big and negative. Yeah? However, notice what's happening. So what we're doing here actually is this is the dot product. So I take this 0, and all of this is multiplied by 0. 0 times this. Yeah? Then I take the next one, and all of this is multiplied by 0. And I take the final one, and all of this is multiplied by 1. Not this, by the way, like I'm multiplying the log of these things. So what that means is, this, and then at the end, I'm adding up everything. So I'm adding up this plus this plus this. That's the dot product. So look what's happening. This is, 0 times whatever, it's still 0. This is 0 times whatever, it's still 0. This is 1 times whatever. So this value is the one that counts. And in general, whatever, the one value is, whatever the positive class is, that is the one that counts. So the way to think about this algorithm is before, when we just had, binary cross entropy loss, then we wanted to make sure that 1, if you have, the positive label, then the prediction is close to a 1. And we wanted to make sure if you have the negative label, the 0 label, true, false, then the prediction was close to 0. In this case, we're like, yeah, whatever, you know what? Do you, with the cars and stop signs, that's not what we care about. In this image, we're looking at the pedestrians. So just make sure that you get this right. And you can see here, this algorithm got it wrong. It was like 0.01. No, that's not it at all. So this algorithm is going to get a huge shock. Even though we don't care, oh, it's actually predicting these other things as well. We don't care. The reason why this makes sense is intuitively think about it. Let's say you have like 500 different output classes. It's going to be really hard to make sure the algorithm, predicts every single class as false when it is false and, true when it is true. It doesn't have to just, learn one relationship. It has to learn 500 of them. But with this, we can say, yeah, you know what? I don't care, like whatever you're doing up here, because it's going to be multiplied by 0. Whatever you're doing up here, then it's going to be multiplied by 0. All I care about is make sure you get the positive class right. Is that making sense? So remember, it's a dot product, which means we're going to multiply all the elements together and then add them up. So that means we're going to turn these scalars into a vector. Sorry, we're going to turn these vectors into a scalar. So let's say in this case, we get out a big value like, negative 200. Why not? Yeah. So that's for this example, I. We're going to sum up all of these scalars across all of the examples. Then at the end, take the average. And again, we're getting back negative results. We're going to multiply by -1, so we get positive results. I hope this is making sense. So again, cross-entropy loss, it's for multi-class classification. Over here, binary cross-entropy for binary classification, mean squared error for regression. I will, as ever, leave you two functions, cost functions to research yourself. They're called the softmax and NLL loss functions. This stands for negative log likelihood. I'd say the more important one that we're going to be using often is softmax. We're going to be using it a lot with neural networks, so just keep an eye out for it. We're going to, explore neural networks soon. So those are ones for you to research. Again, negative log likelihood. Cool. All right, that's part 2 done. One last part and we're all good. We're done. The last part, as I mentioned, is different optimization algorithms. So far, we've only learned about one. The one that we learned about is batch gradient descent. Now, I didn't call it batch, okay? I just called it gradient descent, but technically it's batch gradient descent. What batch gradient descent means is treat all your examples as a batch and make one update. So I'm going to show you the equation. You've already seen it. It's what I called gradient descent earlier, but it's technically batch gradient descent. So you see here, we have our equation to do gradient descent. You saw it up above. Of course, this could be, not the sigmoid function. It could be another function. But the key part is this. We are averaging over all m examples in our batch. So imagine, these days we have hundreds of thousands and millions of training examples. Not only do you have to go through all of the data parameters from 0 to n, a neural network can have millions of these, then you have to go and calculate this for 1,000,000 examples. That's like 1,000,000 squared. That's a lot of calculations to make. And all this so that we can do one step of this. So every single time we're running our gradient update, we're updating our theta parameters. Remember, this is like a storage container for all of these derivatives from, theta 0 to theta n-1. We're doing all of this with millions of parameters, millions of examples on every single step of our gradient descent. So that's why it's called batch, because we're treating all of the examples as a batch. This is very computationally inefficient when you get to large training sizes. By large, I mean usually over 10,000 training examples is when you'd want to consider, using another algorithm, not sum over all of the examples and then take the average on every single gradient descent step. But definitely, if you have m is less than 2,000, use batch gradient descent. So you have less than 2,000 examples, use batch gradient descent is fine. The issue is with large data sets. So what do? It's computationally inefficient, fancy word for it takes just too much processing power to do batch gradient descent, where we go over all of our examples as a batch and then make one update. And we might make hundreds or thousands of these updates. So that's really hard. What's the alternative? Let me give you like the starkest alternative. So starkest isn't just like the most extreme and opposite spectrum. We call it stochastic gradient descent, SGD, where we make one update per example. I'll explain stochastic, it just means random. I'll explain why we call it random gradient descent in a second. But here's the equation. So you see here, for one, partial C by partial theta J, we would go over all parameters 0 to n, and we're computing the same thing, except no more summing over all of m examples. So we do this for one example, the ith example, and then we get, all of these terms from 0 to n, plug them into our big storage container, and then we make one update. So one update per example. Up here, one update per m examples. See the difference? So this is a lot, easier for the computer to calculate, because it just has to do it for one example and then it can make an update. I'll show you now why this is called random, random gradient descent. So let's say we were doing gradient descent here. This is a surface that is a visual representation of, one parameter on this axis, theta 1. Maybe it's like this horizontal axis and then one parameter on this vertical. Yeah? And the height is the cost, C. Sorry, that should be theta 2. There we are. That's 2. So this is just like a simplification because obviously you usually have more than 1 and 2 parameters. However, I'll show you what batch gradient descent would do. Because it's averaging over a bunch of examples, then it's going to have, a more accurate picture of how do we update the parameters so that overall we're doing better. So in general, it's going to go towards the direction of, steepest descent. So let's say it goes here, then here, then here, then here, and here. So it took like 1, 2, 3, 4, 5 steps, and in each step, it was going towards the direction of steepest descent. It was very accurate at figuring out what is the best way to optimize all the parameters. Yeah? Now take a look at stochastic gradient descent. It just knows what is best for each and every one example. So it's going to do like and it might go over here and then over here. It's like a honeybee, and like it'll wander around over here and over here, and maybe like it ends up over here for no reason at all. Maybe it keeps on wandering over this area for a bit, and it might hopefully end up over here, but it might not always. So the thing to keep in mind, the reason why we call this stochastic, I'm not going to get technical here, but two key parts are that one, well, look at the shape. So if you have like a honeybee thing, then it looks a lot more random than a controlled, process of descent. Another key trait is that we don't know how things will end up. With gradient descent, we have a pretty clear idea what the algorithm is going to do, and we have a pretty clear idea that the algorithm will end up at a minima. Might not be, the lowest cost, but it'll be a pretty good low cost. With gradient descent, it might, randomly end up, one example leads it over here, and then it will spend all of its time just wandering around. And it will keep on changing, there won't be like a point of convergence, just because when it comes to um, stochastic gradient descent, each example, you can imagine, each example wants something different. Each example has a different set of parameters. So it will always keep on moving. Hopefully just like a little bit, but it will always keep on moving. So the trade-off is with batch gradient descent, it's pretty simple. However, it's very computationally efficient. So it takes a lot of resources, but gets the right answer pretty predictably. Over here, does not take a lot of resources, but is a lot, more random. Might not get us the right answer. So the solution is, well, one solution is what we see here. If we're running stochastic gradient descent, we want to initialize the parameters, a bunch of times. We might start off one place here, we might start off one place here, we might start off one place here, and over a bunch of iterations, see, what is the lowest possible cost. So here, we might say theta 1 is 0.1 and theta 2 is equal to 5. But over here, we might say, okay, theta 1 is equal to like 5 and theta 2 is equal to 0.1. So we want to, pick different samples. We want to use random initializing points of our parameters so that over time we can do like a bunch of stochastic gradient descent runs. Yeah, that's one solution. Another solution is what we call mini batch gradient descent, where we basically just do like one update per blank examples. So it's like a halfway point. So maybe you don't do like a million examples, or maybe you do 10, you want to have a better idea. So mini batch gradient descent relies on a particular batch size, which is a parameter we can adjust. So we might have like 32 examples in our batch size. We might do 64 examples in our batch size. And it looks pretty similar to, um, batch gradient descent, except we're not going over all m examples, we're just going over batch size examples. So maybe 32, maybe 64, maybe 128, but not like a million. Yeah? So it's like a halfway intermediary between, okay, you have, very random motion everywhere, and you have controlled, measured gradient descent steps. So over here, we have this as a hyperparameter, another hyperparameter that would have to tune, just like our learning rate alpha over here. By the way, just, a Python tip. While you're doing this, you actually need to generate the batch sizes and select, specific examples. Then look into this for I in range and what happens when you pass in 3 parameters to the range function. So I'll leave you to explore that on your own when it comes to how do you actually implement, mini batch gradient descent, but this will be useful for you. Cool.
Wait, so I had a question. Uh,
Mm-hmm.
has it been done where like you can start off with the optimizer with stochastic gradient descent, and then when you get to a point where like loss is less than 0.3, you can switch to gradient descent, or that's not a thing?
I think it would have been done, especially because, you can run multiple iterations of the algorithm one after another. So let's say you have like stochastic gradient descent and it goes like over here and over here, and then over here, you have, a set of saved data parameters, right? So the data parameters you get out of gradient descent, they will be saved. And then maybe later you want to do like batch gradient descent to finish off the process.
Yeah.
Yeah, I'm sure like someone's done it. I don't know the exact name for that approach, but if you want to search it up, I'm sure you could find something. So that is almost the last thing. I will introduce one last concept to you, and then we're done. So when it comes to different optimization algorithms, then one way that they vary is by the number of examples you process at a time. Do you process all m examples? Do you process one example? Or do you process somewhere in the middle? However, there's like this entire other world of variance where you have these different formulas that we use for the parameter updates. You still have, the gradient computation, but we might have different formulas that we use. I'll show you one formula. You can search up some other ones that I'll link to. So one algorithm that I'll show you is gradient descent with momentum, technically mini batch gradient descent with momentum. And the way that this works is it uses another approach to smooth out, this random variation stuff of, let's say, a small batch size or stochastic gradient descent. So what it will try to do is, if we have the algorithm going in all these places, then it'll try to plot the average path so that you still, you aren't affected too much by all these variations. Is that concept making sense? So it'll try to plot the average path smoothly so that you're not affected by all of these variations as much. Is that concept making sense?
But to find the average path, you first have to go through the whole stochastic gradient descent, right?
Yeah.
No.
So you'll see with the equations how we're going to do this.
Okay.
So that's the general idea of the algorithm. Find, an average path that doesn't have so much randomness and noise. It's not so spiky. I'll show you the way that we do this. It's with a concept from statistics, actually. It's called an exponentially weighted moving average. Fancy word, but it just means, take a running average. Here's how it works. So you have, different time positions, t. So your average at the current time position t, it's going to be this hyperparameter beta times the average at the last position plus 1 minus beta times the average at this position. Here's the way it kind of technically works. So beta is always close to 1. So basically this is equal to 1. It's almost always equal to about 1. Not exactly 1, but about 1. And then 1 minus beta, well, that then becomes about 0. Yeah? So the old average, the old value that we have, it turns out being big because we're multiplying it by almost 1. And the new average that we have, the new value that we're getting, it becomes very small because we're multiplying by almost 0. I'll give you a theoretical, concept of this. So let's say these are, values that we have. This is time t. So, values that we're getting over time. These are pretty spiky. So if we just join them with straight lines, that would kind of be like the graph you saw earlier, where you just, go spike, 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 spike. However, we can be a little bit more smooth about this. We want to round out all of these averages. How are we going to do that? Well, if you look at this formula, so what we do is we start off average t. We start off at t is equal to 0. So let's say over here we have 0, and this is t. We say, okay, starting off, the average is just going to be equal to 0. So we say average at position 0 is equal to 0. Yeah? So it starts off as the average is 0. That makes sense. We haven't added anything to it. As we add the first thing, then the average moves from 0 towards this first thing. However, remember the old is big, the new is small. So the average only moves a little bit from 0 towards this thing, not all the way. Then you get, it's moving a little bit more because this example is increasing further. It's moving up a little bit more because this example is increasing further. Then it stays the same because, this example, it's not changing. And now it's going to increase a little bit more, but not as much as, up here, because remember, the old is big, the new is just a small change. And then it'll decrease a little bit because, this one is decreasing, but it's not going to decrease too much. Old big, new small. And then it won't change because, the average that it has reached is equal to the new point. So now look, you went from the yellow spiky thing to this blue pretty smooth thing. Yeah? Here's a less theoretical example. So you have these data points. This is from like a Australian poll. You have like these X crosses. You see all these crosses? These are like data points. You can see they vary a bunch, but we just draw like a moving average throughout them to smooth out all the bumps. Yeah? Now, how can we apply this to, remember, the thing that was spiky in this case, it was all of these derivatives. All of these derivatives were what were always changing with stochastic gradient descent. So instead of the values being like, votes, that's what we got in this case. The values that we were smoothing out were votes over time. In this case, we're going to do derivatives over time. So look, on iteration t, so this is the iteration of gradient descent. First, we compute the derivatives. So these are all, this is a storage container for all of the derivatives. Then we're gonna create this special value v, where v is equal to, the previous value from position t minus 1. So this is iteration t, this is t minus 1. Again, we initialize v0 as 0. We're going to multiply it by beta, which is almost equal to 1. And then we're going to add, this new derivative. So what that ends up doing is this old bit becomes bigger. It has a bigger influence on the average. This new bit has a smaller influence on the average. So visually, if you have, if you have, if you have like a stochastic gradient descent doing its thing, then even if, the second example goes like a lot in this direction, it's not going to sway the moving average too much. Same thing here. All of these individual like kinks, they won't change the average too much because we're not, going to go in every extreme direction. We're saying, okay, whatever new derivatives that you get, whatever new values you get, those are only going to affect a small bit because of this term. The main components will be, the previous derivative value. And in the end, we're just subtracting this previous derivative value, this previous, moving average of the derivative, instead of directly subtracting this derivative. Up here, directly subtracted the derivative. Now, we're not directly doing that. We're, keeping a moving average of the derivative. This approach is called gradient descent with momentum. Because you can think of it like, hey, whatever examples, you're not going to change my momentum. I'm going to go in like my general direction. Making sense?
Yeah, so it's kind of like stochastic gradient descent, but like with a small learning rate, so it doesn't get swayed too much.
Yeah, you could think of it like that. You could think of it like that.
Okay, cool. Got it.
The difference is we're still going to be like with the small learning rates. If alpha was really small, then theta would take a really long time to update. However, in this case, theta doesn't take a long time to update, because even though we're getting the benefits of like not an extreme, derivative, we still get we don't get the drawbacks of having slow gradient descent. Cool? So if you're ever, running mini batch gradient descent or stochastic gradient descent, do it with momentum. Now you know about it. There are also these algorithms called RMS prop and Atom. Atom is very famous. It's used a lot. They're based on this principle. They're based on this principle. So I've given you most of the new math you need so that you can understand these. Maybe it might be a bit difficult because there is one, the equations might look a little bit complicated, but I think you might, be able to figure it out. So you can search up how these optimization algorithms work and the equations that they use. Keep in mind now we do have like a lot more hyperparameters. We have this alpha, we have this beta, and beta, and we also have the batch size. So these are all things that we have to adjust manually now. How do we adjust them in the right way? That is the subject of the next lesson.